Hello everyone, I'm Anas and I'm a PhD student at Télécom Paris. So today I'm very pleased to give this talk for the second symposium on machine learning and dynamical systems. And today I'm going to present you my joint work with my supervisor, Professor Pascal Bianchi. And this is going to be about the convergence and the dynamical behavior of a very famous algorithm called the Adam algorithm in the context of non-convex stochastic optimization. So here is the outline of the presentation. First, I will try to introduce quite smoothly the Adam algorithm, which was proposed by Kingma and Ba in 2015. And then, in order to analyze this algorithm, I will introduce a continuous time version of Adam, which will be a relevant approximation of this Adam algorithm. So we will analyze its convergence properties and dynamical behavior. And afterwards, we will look at the original Adam algorithm, so in discrete time, with the constant step size. And finally, I will introduce a variant or a new version of the Adam algorithm with decreasing step sizes and analyze its behavior in discrete time. So here is the general formulation of the problem we want to solve. So we want to minimize a function capital F of x, which will be our objective function. So this function writes as the expectation of a small function f of x and xi. So here, a small f can be seen as a loss function of a model parameter x. So x can be the parameter of your favorite machine learning model, and xi should be seen as the data points. So you can also think of x as the weights of the neural network you are trying to fit, or the weights you are trying to optimize. So the general assumptions in this work will be the following. So f as a function of x is possibly non-convex. So it's not supposed to be convex. And it is differentiable so that we have access to a gradient, and so that we can use some gradient descent methods, for example. We will see this in a moment. And we also assume some regularity assumptions to define the function capital F as an expectation, and to also define the gradient of capital F. So here we need to, for example, to exchange the expectation with the gradient. So these are technical assumptions that we are not going to detail here. And we also suppose that we have access to a sequence xi n of IID copies of the same random variable xi. So here xi has an unknown distribution that is revealed online through the sequence xi n. One classical solution to solve such a problem is to use the workhorse stochastic gradient descent. So here you follow the opposite direction of the stochastic gradient here, and you use a step size gamma n, which may depend on the number of iterations n, and which is the same for all the coordinates. So two limitations of this method are the following. The first one is the choice of the learning rate. So if you choose this gamma n too small, you will have a very slow convergence. If you use it too large, so we'll have fluctuations of your estimate, large fluctuations of your estimate. So you have to choose it wisely. And the second point is that here gamma n is used as a common learning rate for all the different coordinates of this gradient. Whereas there might be some discrepancies between the different coordinates of the gradient, and you may use different, or you may want to use different step sizes for different coordinates of this stochastic gradient. So this brings us to the family of so-called adaptive algorithms. So this family of algorithms, so Adam is a particular case of this family, presents three differences, big differences with the stochastic gradient descent algorithm, the standard one. So the first one here is that instead of using a step size gamma n, which is the same for all the coordinates of the gradient, you will use gamma ni, which is a step size which depends on the coordinate. So see the first difference. The second one is the fact that instead of using a constant step size gamma or a gamma n, which is 1 over square root of n, for example, you will use, in adaptive algorithms, a gamma ni, which is a function psi, so some function which we do not precise here, of the past stochastic gradients. So here we see that we use all the history of past gradients in order to define a step size gamma ni, which is used in the adaptive algorithm. And the last point is that instead of using the stochastic gradient here, in adaptive algorithms, we use an estimate of the gradient. So here it's GNI. One example of such algorithm is RMSProp. So this is an unpublished optimization algorithm which was proposed by Hinton in some lecture notes. So, and it's a coordinate-wise step size. So here you see that we have an effective step size here with a step size gamma 0 fixed. And this effective step size in red depends on Vn, and Vn itself depends on so the square of the gradient. So here the square is of course coordinate-wise. And we see that so that Vn, or the effective step size, depends on some past gradients. So here we have a kind of memory, and Vn is an exponential moving average of this squared gradient. So here is an example, an illustration on a very simple optimization problem, which is a linear regression, 2D linear regression problem. So here we have the objective function represented by its level curves. We have the optimum here in dark, so it's the cross here, the optimum. We start from the same initialization point, and we see that by whereas SGD takes a different path here, which is not straightforward, not straight to the optimum, we see that RMSProp, which uses some coordinate-wise step size, takes a very direct or very straight path towards the optimum. A second ingredient which we will need before introducing the Adam algorithm is what we call the momentum or the inertia. So we know in the literature that it's in general used for acceleration purposes. So when we hope for acceleration. So for example, in the strongly convex case, we know that heavy ball proposed by Polyak achieves some acceleration upon the standard gradient descent in the strongly convex case by reducing the constant in the exponential convergence rate. So we have a square root of the condition number instead of just the condition number in the exponential speed. So here, of course, we do not have any guarantee about this. However, the momentum is used in practice, and here is the iterates. Here are the iterates. So Mn is an exponential moving average of the stochastic gradient, and instead of following the opposite of the gradient, you follow the opposite of this Mn sequence. And if you just rewrite the iterates here, xn, you see that you follow the opposite direction of the stochastic gradient, and you have an additional memory term or momentum term, or also seen as inertia, since we use the difference between the xn and xn minus 1, which is added to the current iterate. And in a similar illustration here, we see that instead of having some stochastic gradients which are very oscillating here, so we see that the exponential moving average smoothes this stochastic gradient, and we have a path which is more which goes straight to the optimum here in Y. And the last ingredient, because before going into the Adam algorithm, is what we call debiasing. So during first iterations, the sequence Mn is a biased estimate of the gradient of f at x0. So here is the update rule of Mn. If you unfold this update rule and replace this stochastic gradient by its expectation plus some noise here, so we have some noise that we're going to detail. And if we suppose that the gradient of capital F here is very close to gradient f of x0 during the first iterations, so you see that here the sum of the alpha to the power n minus k will give you 1 minus alpha to the n. So we see that we have a biased estimate of the gradient. And in order to debias this estimate, we will divide by 1 minus alpha to the n. And this Mn divided by 1 minus alpha to the n gives you exactly this expression using the stochastic gradients. And you can observe that you have a convex combination of past gradients here with some exponential weights here, alpha k, where alpha is fixed and close to 1. So this is what the debiasing step is. So combining now RMSProp with what we saw with the momentum and then finally the debiasing steps, you get the very famous Adam algorithm, which is used very famous in deep learning applications. So it was proposed in a ICLR paper in 2015. It has more than 50,000 citations in Google Scholar, and here is the algorithm. So we have this momentum Mn, momentum sequence. We have a Vn, which is an exponential moving average of the squared gradients, so coordinate-wise square. We have the debiasing step for Mn and for Vn, and finally here is the main update. So Xn, we follow the opposite direction of M hat n, and we have here this effective step size with what we will call the step size gamma, which is fixed along the algorithm, and this V hat n, which depends on the path of the stochastic gradients. And of course here alpha and beta are fixed, and the initialization is x0, some x0 in RD, and m0 equals 0 and v0 equals 0. Of course, we are not the first to explore the convergence guarantees of this Adam algorithm. So there are some related works. So in 2011, Dushi and his co-authors proposed the ADA-GRAD algorithm, and they proposed a regret bound for this algorithm. A few years later, Adam algorithm was proposed with a regret bound in the convex case, so in the conference ICLR 2015. And a few years later, so in 2018, Reddy and his co-authors proposed a counterexample to the regret bound proposed here for Adam, and they proposed a fix under the form of a new algorithm, IMS-GRAD, which has some decreasing effective step size here, and so they recover this regret bound not for Adam but for this IMS-GRAD. So we observe here. Let's note here that this counterexample, of course, does not apply to our analysis. Our assumptions exclude this counterexample. And in 2018, so the same year, so we started to look at this problem in 2018, and in the same year we saw Basu et al. Proposed a noiseless version, so without any stochastic gradient, but they use some specific parameters of the algorithm which do not really correspond to the practice. And Chen et al. Proposed also some stochastic guarantees, some interesting results, which apply easily to IMS-GRAD and ADA-GRAD, but which are not really easy to generalize to the Adam algorithm. Of course, there are a lot of more works, even in 2020, about this question of the Adam algorithm and its convergence guarantees, but there are no almost sure convergence results, for example, for a decreasing step size, and no clear convergence results. Although this is a counter result proposed by Reddy et al. So let's go into this continuous time version of the Adam algorithm. So in order to analyze the Adam algorithm, we will use what we call the ODE method. So this is a quite old method, which dates back to the 1970s, 1977, with the work of Jung, and with further works of Kushner and Yin. So some results are compiled in this book, in this textbook of 2003. Of course, there are a lot of more references using this method and applying it. We will see some of them later. So here's the idea. You have the Adam algorithm has needs three different sequences. Xn, think of the weights of your neural network. Mn and Vn, which are used to construct Xn. So we will denote by Zn this triplet. And the idea is the following, that for each gamma here, step size gamma, you have a new iterate, Z1, Z2, etc., and so on, or n gamma. And the idea is to interpolate linearly the different iterates here, so that we have a curve. So a piecewise linear curve. And the idea is that when gamma goes to 0, when gamma gets small, this trajectory will be close to a continuous time one, which will be the solution to an ordinary differential equation. So more formally, let's see what it gives us. So here is the algorithm we have, the update rules. You have a Zn, which is the algorithm, which uses the past iterate Zn minus 1, plus gamma times this quantity here, which depends on the previous iterate, explicitly on n because of the debiasing step, in our case, in Adam, and psi n the noise. We introduce the expectation of this quantity with respect to the past, so with respect to the sigma field of psi 1 to psi n. And we introduce delta n, which is just the difference between h, capital H, and small h of gamma, which is the expectation. And we end up with the following decomposition in a mean field, here, h gamma, and a martingale noise, which is a martingale difference sequence. And when we rewrite this expression, dividing by gamma here, we see that we have a kind of discrete derivative here. We have a mean field, so the behavior of the algorithm will be encompassed in this one. So this is what we call the drifts. So this is going to control the behavior of the algorithm. And then you have a noise term that we will have to control in order to control the algorithm and the convergence properties of the algorithm. So let's see what it gives us exactly for the Adam algorithm. So we have three different sequences, Mn, Vn, and Xn. When you rewrite the update rule of Mn, you have this discrete derivative here divided by gamma. And you have two different terms. So here, instead of the stochastic gradients, we replace it by the gradient of the objective function capital F. And you have this additional noise term, which is the difference between the stochastic gradient and the gradient of the objective function. We do exactly the same for Vn with the squared gradients instead of just the stochastic gradient. And in the following, we will make the following hypothesis assumption. So for a fixed step size, so gamma is fixed all along the run of the algorithm. When you choose gamma, you have alpha, which we will suppose depend on gamma. So for a given gamma fixed, you will have an alpha of gamma, which is the hyperparameter of the Adam algorithm. And we will suppose that 1 minus alpha of gamma divided by gamma converges to A when gamma goes to 0. So this is a natural assumption because in practice, alpha is something very close to 1. So it's natural to suppose that alpha converges to 1 when gamma goes to 0. We do the same for Vn and for Xn. And if you compare this system with this continuous time one, you see that they are very similar. And here we see that we have really a kind of analogy between the discrete time system and its continuous counterpart. So here we see where dynamical systems come from. So here we see that m dot, the continuous time version of m, is a, so here a, times the gradient of f minus m. The same for v, where we introduce s, which is just the expectation of the squared stochastic gradient here, s of x minus v as here. And same for x. Instead of alpha to the n, we have something like exponential minus at. So this is exactly the same in continuous time. And we will denote by this field by h of tz. And so here are the assumptions we make to analyze this dynamical system that we just introduced. So we have the assumptions on the model. So we assume some regularity assumptions on the function f. We suppose that it's possibly non-convex, differentiable, and some technical assumptions that we talked about in the beginning. We suppose that the function capital F is coercive. So this is an assumption which is quite mild, and which will allow us to prove some boundedness, the boundedness of the solution to the differential equation, and also which will be useful for discrete iterates. We will see. We will introduce the expectation of the squared gradient, which we will denote by S and suppose it's strictly positive. So this is a quite mild assumption. So the gradient is not always 0 here, the stochastic gradient. We suppose also we make an assumption on hyperparameters. Suppose that alpha and beta are close to 1. So this is the assumption I just introduced in the previous slide. And this is verified, of course, in practice. And finally, the noise, we have access to a sequence psi n of independent and identically distributed variables, copies of the same variable. So here is the continuous time system we obtain, which will be kind of continuous time Adam. So if z is the triplet x, m, and v, you have that z dot equals h of tz. So observe that this system is non-autonomous. This means that it depends explicitly here on t because of the debiasing steps in discrete time. So in discrete time, you see that you have explicitly n in the debiasing steps, and here we have t in continuous time. And the first result we establish is the existence, the uniqueness, and the boundedness of a global solution to this ODE from an initialization here x0, 0, 0, which is exactly the initialization used in practice, under the set of hypotheses of assumptions we've made in the previous slide. And one important remark here is that this result does not stem directly from off-the-shelf theorems. So we cannot, for example, apply directly any Picard theorem or this kind of existent theorem or Cauchy-Lipschitz, because of two technical difficulties here. The first one is that h as a function of x is undefined at 0 because of the, as a function of t, it's undefined at 0 because of this 1 minus exponential minus at, so this is not defined at 0. And h as a function of z is not locally Lipschitz because of this epsilon plus square root of v. Square root of v is not Lipschitz continuous. So we have two different difficulties to handle. So we're not going to the details, but this is the we handle this in our paper. Byproduct of our dynamical system analysis is the following, and it explains why really these debiasing steps are interesting. So these debiasing steps are in green here. So without the debiasing steps, with the debiasing steps, we show that the objective function f along the trajectory x, so xt here is just a continuous time version of the iterates xn which we are interested in. We show that this is always smaller than f of x0, which is a kind of initial guess. So x0 here is the initialization for the sequence xn, and f is the objective function. So here at x0. And here is an example to show this. So we, in a 100-dimensional stochastic quadratic problem, we see that when you use the debiasing steps, you see that here the objective function is always smaller than its value at x0, whereas if you remove the debiasing steps, you see that you can potentially increase the objective function here f compared to its initial value at x here. And so here is one of the main results in our continuous time analysis here. So it's convergence towards the stationary points or the critical points of the objective function f. So this is interesting. So under the set of hypotheses of assumptions here of our model that we've introduced before, we show that x of t, which is the continuous time version of the Adam algorithm, converges towards the critical points of the objective function capital F. So these are the points where the gradient is 0. So, and in order to show such a theorem, we need a key argument, which is the existence of a Lyapunov function for this ordinary differential equation. So this is one of the main contributions of this work. So we define this Lyapunov function, which is the sum of the objective function capital F and an additional term, which can be seen as a kinetic energy term here. So whereas, for example, for just a gradient flow, you will just have capital F here as a Lyapunov function. Here it's a bit more difficult. You need an additional term here, which depends on the m, the continuous time m here, and v also. I'm not expliciting here the expression of u, but you have an additional term. And we show that this function along the trajectory zt of the algorithm is non-increasing on 0 plus infinity. And this is the main argument used to show these convergence results. So now that we have a convergence result towards critical points of the objective function, we're going to be interested in quantifying the speed of convergence or the convergence rate. And one interesting tool to do so is what is called the Lojasiewicz inequality. So this was introduced in 1963 by Stanislas Lojasiewicz, and it was also it is very popular nowadays and used by, for example, Atouche and Bolt in 2009 and even further to analyze a lot of algorithms. So here is the assumption, what we will call the Lojasiewicz property. So for each critical point here x star, we will suppose that the gradient of the objective function has a norm which is greater than some expression here depending on the function value gap. However, observe here that this inequality is valid in the neighborhood of x star. So we do not suppose this inequality everywhere, but instead just in the neighborhood of a critical point x star. So this is very close to what people know as the Polyak-Lojasiewicz inequality, which is very common in the machine learning community, optimization community. So this Polyak-Lojasiewicz corresponds to theta equals 1/2. However, we really insist on the fact that we do not suppose, for example, Polyak-Lojasiewicz or this inequality everywhere, but only on, of course, all the points x star, but in the neighborhood of this x star, and not everywhere. So this is a very mild assumption because it's satisfied for a broad class of functions. For example, semi-algebraic functions, real analytic functions, and if you generalize to the KL, critical Lojasiewicz inequality, in the non-smooth case, for example, it is even satisfied by neural networks with some ReLU activation functions which are non-smooth. So the interpretation of this function is the following, is that f, so the objective function, becomes sharp under a reparametrization of its values. So if we suppose, without loss of generality, that f of x star is 0, for some suitable points x star, which means in the neighborhood of these x star points, if you choose this function phi, which is a polynomial function, you see that this inequality writes exactly as this one. So the norm of a reparametrization of the gradient of a reparametrization of the objective function f is always greater than 1, which means that it does not become small over time. So this will help us quantify the convergence rate. And here is an example just to see exactly the correspondence between the Lojasiewicz exponent theta that we just introduced and the speed of convergence. So in a very simple example here, so f of x is just the polynomial function x to the p. You see that the larger p and the flatter gets the objective function here. And obviously, you will see that when the function is very flat here, the gradient, which becomes very small, so the gradient descent will be very slow. Whereas where the function is a bit sharper here, you see that the convergence is faster here. So we see a clear correspondence between the Lojasiewicz exponent here, theta, which corresponds here to 1 over p, and the speed of convergence and the convergence rate of the gradient descent iterates. And so here are the results we have about the convergence rates under this Lojasiewicz property. So this is inspired by a work of Alain Haro and Mohamed Ali Gendoubi, proposed in 2015. So this work does not apply to the Adam algorithm. However, with some modifications, we can still have very similar results. So under the same set of hypotheses and the Lojasiewicz inequality, this is the result we establish. We first show that x of t converges to a single point x star, which is a critical point of the objective function. So here we have the convergence to a single point instead of just the convergence to the set of critical points. And we can quantify the rate. If theta is this Lojasiewicz exponent of f, capital F, sorry, at x star, we see that x of t minus x star converges to 0 with here a sublinear rate when theta is between 0 strictly and 1/2. And when theta equals 1/2, we have a speed of convergence of which is exponential with some delta here, for some delta. Now that we have an analysis of this dynamical system, we will move to analyze the constant step size algorithm, which is the original algorithm. So here is the set of, I'm just recalling the set of assumptions that we had before. So model, regularity assumption on F, the coercivity of capital F, which we will use, which we already used in the dynamical system analysis and we still keep here. The expectation of the square is denoted by S. We have some hyperparameters assumptions which mean that alpha and beta are close to 1. So these are the hyperparameters for the exponential moving averages. And the noise, for the noise, we have an IID sequence psi n. And we add this regime hypothesis that we use constant step size here in our analysis. So here is the first result we can establish. So by using some techniques which we find in which we can find in Benaim and Schreiber 2000, we can show what we call the weak convergence of the interpolated process. So this is the linearly interpolated process that we've talked about before. So between the iterates, we just interpolate linearly the iterates. And we make this assumption, this moment assumption. So this is a control of the stochastic gradient. So we suppose that we have this moment control. And under this assumption, we can show that here the distance between the interpolated process, which is here indexed by gamma, which is the fixed step size, and the solution zt of the ODE, so the distance between the interpolated linearly interpolated process of the iterates, and zt, which is a smooth curve, which is the solution to the ODE. So this distance does not, so is small with high probability, which means that the probability that this distance becomes greater than delta for any delta goes to 0 and gamma goes to 0. Of course, gamma is fixed along the iterations. This is a theoretical result which tells you that when gamma goes to 0, then you have this probability which becomes small. So this means that the ODE that we've proposed, or the solution to this ODE, is a relevant approximation of the Adam algorithm in this exact sense. So just this quick simulation to show that this result, to illustrate the previous result. So here we have the Adam algorithm in blue. We have an objective function which is represented by the level curves of the function, and ODE solution which was computed by an Euler scheme, summation scheme, and you see that you have a kind of ODE solution which is shadowing the iterates, or the iterates are shadowing the ODE solution. And we just have here SGD for comparison, which is taking a different path. So this is on a 2D linear regression. And so here is the main result for the constant step size algorithm. So we establish a long-run convergence of the Adam iterates by using some techniques proposed in Theorem Pages and Bianchi et al. 2019. So the first observation here is that since the step size gamma is fixed, we cannot achieve any almost sure convergence of the algorithm because of the noise. So we will bounce around the optimum because of this noise which moves you from the optimum. So we will consider this regime where n goes to plus infinity and then gamma goes to 0. And here is what we can establish in this particular regime. So under the previous assumptions and the moment assumption to control the noise, we add a very strong assumption here, which is the stability assumption. So we suppose that we have a kind of tightness here of the Zn gamma, C indexed by n and by gamma. This process is supposed to be tight in the probabilistic terminology sense. So we suppose that a kind of boundedness here. So this assumption is very strong. Of course, it's very difficult to verify in theory, but in practice, you can suppose that you have a kind of projection step onto a compact set, so that you can verify this. But under this assumption, you show that for all delta, the probability that the distance between x and gamma, so here are the iterates indexed by gamma, and the set of critical points of the objective function, so the probability of this distance to be greater than delta goes to 0 in mean when n goes to plus infinity and then gamma goes to 0. So this is a desirable, of course, result concerning the iterates with constant step size. So now we are going to move to the decreasing step size case and analyze Adam in this particular regime. So here is the algorithm. There are some differences with the previous one. The first one is that instead of using alpha and beta, which are fixed, now we use alpha n and beta n as hyperparameters, and of course we use gamma n, which is a decreasing step size, instead of just a fixed gamma as before. So here, because we use an alpha n and a beta n, we have to change, of course, the debiasing steps. So before we had here 1 minus alpha to the n. Here, since we have alpha I, so we have the product of the alpha i's. This is just easy or obvious difference. So we use the debiasing steps here. This is just an online update of Rn instead of using this for formulation. And we get exactly the same algorithm with these differences. We will suppose also that with the exact same of assumptions here, H model, we will suppose moreover that 1 minus alpha n divided by gamma n goes to A, and 1 minus beta n divided by gamma n goes to B, similarly. Which means that alpha n and beta n are close to 1, basically. So in order to analyze this algorithm, we will consider what we call Robbins Monro schemes, and we will see how can we move from a Robbins Monro scheme to some dynamical systems. So here is consider here the update rule of a given algorithm, stochastic algorithm, whenever it is, wherever it is. So yn plus 1, whatever it is, so yn plus 1 equals yn plus gamma n plus 1. Here we have the drift term g of yn plus a martingale difference sequence mn plus 1 and a bias term which will be supposed to converge almost truly to 0. We have a sequence of deterministic step sizes which are non-negative, converging to 0, and such that their sum is infinity. So, and we have a martingale difference sequence noise. So we can interpret this sequence as a noisy discretization of this continuous time system, which is the solution to an ODE. So here y of t, y dot of t equals g of y of t. So g here determines the behavior of this dynamical system, and of course drives this discrete time system. And this assumption here, which is very classical in stochastic approximation, means that the time can go to plus infinity. So the sum of the gamma k go to plus infinity, is plus infinity. And the question we are asking now is the link between the asymptotic behavior of this sequence yn and the ODE, or the solution to this ODE. So the answer, of course, comes with the ODE method in stochastic approximation. So there is a huge literature on this ODE method. We've, of course, already talked about Young and Kushner and Yin. There is also Marie Duflo, Michel Benaim, Vivek Borkar in 2008, and a lot of more references, Benveniste and Priore, which were interested in this ODE method. So informally, this is the idea. So this is a very, very important idea and very essential idea in our analysis. So informally, when gamma goes to 0, gamma n goes to 0, the noise washes out. And the idea is that the limiting behavior of yn will be the same as the limiting behavior of yt, which is the solution to the dynamical system. So here we see that informally, the asymptotic behavior of yt is the same as the asymptotic behavior of the sequence of our algorithm yn. A bit more precisely, this is exactly what we show. So if you consider yt here to be just the linearly interpolated process, so just joining the dots or joining the iterates with the lines, we show that this yt is what we call an asymptotic pseudo-trajectory of the flow, or of the solution of the ODE we are considering. So this means the following, that this yt approximates the solution to the dynamical system here, phi s of yt. So this is the solution at time s taken from yt. So yt approximates the solution to the ODE with arbitrary accuracy, so this is what this means, and on windows of arbitrary length, so for all t here, strictly positive. And it is shown, for example, by Benaim, that with this property we can show that we will have similar behaviors of the continuous time dynamical system and the algorithm we are considering. And in order to show this, you need a control of the noise and a boundedness of the sequence yn you are considering. So here the result we get for the almost sure convergence. So our algorithm, which is Adam, for example, writes exactly, we have a decomposition of this algorithm as follows. So here we have h infinity, which is the limit of h of t zt. Well, I'm not detailing here this, but we have a function h infinity, which is the mean field. We have a noise term here, eta n plus 1, and a bias, which is shown to be converging to 0 almost truly. We make the following assumptions, which are very classical. The first one on the step size, very classical in stochastic approximation. We have an additional assumption on the noise here, so it's a moment assumption here. And the final one is a strong assumption, of course, is the stability assumption. We suppose that we have that the iterates Zn are bounded with probability 1. We will see how we will handle this hypothesis. So under these assumptions, we show that xn, as in the continuous time system, so exactly the same way, xn converge to the critical points of the objective function. And we can even show the convergence with probability 1 to a unique point if the set of critical points is finite and countable. So now we just handle quickly the stability assumption that we've made, that the iterates are bounded with probability 1. So we can show this result actually by adding this assumption. So we suppose that nabla f is Lipschitz, and that we have a growth assumption here. So here, the moment here, the second moment is controlled by the objective function. It's upper bounded by this quantity. Under these assumptions and some hyperparameter assumptions I'm not detailing here, we show that this sequence Zn is almost surely bounded. And in order to show this result, we just adapt our Lyapunov function to discrete time. So we show that in a certain sense, the discrete derivative of our Lyapunov function has the same behavior as in continuous time. So the proof is very technical, so there are a lot of computations and calculations, but basically this is the idea, to show that this Zn is almost surely bounded. So now that we have the convergence towards critical points, we can be interested in analyzing the fluctuations of the sequence Zn around Z star, which is the critical point we had. So our algorithm writes as this, as we've seen before. And we introduce a rescaled algorithm here, which is just Zn plus 1 minus Z star divided by square root of gamma n, which is the step size, which is supposed decreasing and under the form here n to the power minus kappa, with a kappa between 0 and 1. If you inject exactly this equation here into the rescaled algorithm, you will get something exactly like this. So this update rule of the capital Zn. The first remark here is that instead of getting gamma n plus 1 in front of the noise at eta n plus 1, we have square root of gamma n plus 1 because of this division. So here we see that the noise is amplified. We have what we call a strong noise. So this is the first point. The second point is that this quantity, can be estimated as a function here of gamma n, so we can do a asymptotic development of this. And the third point is that this h infinity of Zn, we can simplify it, or we can do a Taylor expansion of this Zn around, of course, Z star, if we are close to Z star. So this is the Taylor expansion. And by combining these 3 points, we get this update rule. So Zn plus 1 equals the identity plus gamma n plus 1. A matrix H bar here, which depends on the Jacobian here of H infinity at the point Z star, plus some sequence Bn plus 1 bar, which is not the same as this one, so a different sequence, plus what we call the strong noise. So why this is interesting? So this is interesting because we have some theorems to analyze this kind of strongly perturbed stochastic algorithms. And here is the result we use. So this is based on what is called the stochastic differential equation method, so SDE method, that you can find in the work of Peltier and Duflo in 1996 and 1998. So here's the algorithm. So when you have an algorithm, as we've seen before, with a matrix H bar which is stable, which means that the largest real part of the eigenvalues is negative, we can show that this sequence Zn, under some hypotheses here, goes or converges in distribution to a distribution mu, which is the unique stationary distribution of the process x of t here, which is the solution to this SDE. So here you see that we have a drift term here driven by the matrix H bar, which is stable, and a diffusion term here. And so mu has a Gaussian distribution with mean 0 and sigma bar here, the covariance matrix, which is a solution to the Lyapunov equation. So what are the assumptions that we need in order to achieve our result? The first one is an assumption in order to have the Taylor expansion. So here we suppose that f is C2 and that the Hessian of the objective function at x star is positive definite and that S is C1. So this helps us to have the Taylor expansion we've just talked about before. We have some hypothesis on gamma n. So gamma n writes as gamma 0 divided by n to the power k, to power kappa. And finally, we have a moment assumption here, which helps us control the noise. So this is a bit stronger than the assumption we've made in the almost sure convergence results. So we have a bit more than 4 here than before. And under these assumptions, if we suppose that the probability of Zn to go to tend towards Z star is positive, we have a conditional central limit theorem which shows that this rescaled algorithm converges in distribution to a Gaussian distribution with mean 0 and covariance matrix, where the covariance matrix is the solution to this linear system, which is called the Lyapunov equation. And now what is interesting is that this Lyapunov equation, which is a linear system, can be actually solved. So we can exactly compute this sigma by a trigonalization of the matrix H. So H here is the Lyapunov function of the mean field, the Jacobian of the mean field. H infinity at the point Z star, we can compute it. We have something like this with a lot of zeros, and with D, which is a diagonal matrix here, depend on the function S at the point X star. So we can trigonalize this and solve this Lyapunov equation to obtain the exact form of the asymptotic variance formula. So this is the variance, the asymptotic variance. So we omit here the expression of C. We see that the variance depends on the eigenvalues of something which is very close to the Hessian. And we have P, which is a change of basis matrix. So why are we interested in this? So the idea is that the following question is: can we reduce the asymptotic variance? Can we play on the hyperparameters of the algorithm here to reduce the asymptotic variance? So can we play on A, for example, or on B, or these parameters? So the first remark regarding this question is about the influence of B and Vn. So here, as you can observe it, there is no B. So B has no influence on the algorithm. However, Vn, of course, has an influence, but only through this matrix D that we see here. So D is defined using S of X star. S, of course, is the expectation of the squared, and Vn is defined using the squared gradient. So S, of course, is related to V. But Vn, the fluctuations of Vn have no influence on this asymptotic variance of the stochastic of the Hadamard stochastic algorithm with decreasing step sizes. And the interesting observation, so what we show, is that sigma 1 here coincides with the limiting covariance of this algorithm, which is a simple, quite simple algorithm. So it's a kind of preconditioned stochastic heavy ball. So we take stochastic heavy ball here when D equals identity, and we add here a D matrix, which is exactly this matrix here. And when you look at the limiting covariance of this algorithm, you have exactly this sigma 1. Of course, this algorithm is not implementable because D depends on X star, so you don't have access to this optimum. But this is interesting to see that B has no influence, and Vn, the fluctuations of Vn do not influence the asymptotic variance. And finally, regarding the influence or concerning the influence of A, of the hyperparameter A here, we see that we have this development or this asymptotic equation. Sigma 1, so the stochastic variance, the asymptotic variance, can be written as A asymptotic variance here with, which corresponds to an algorithm without any momentum, plus a second term here, which depends on a matrix delta and a big O of 1 over A squared. So what is interesting here is that maybe we can choose A. We may choose A in order to reduce the asymptotic variance here, sigma 1. However, the problem is that this matrix delta is neither positive definite nor negative definite, which means that the influence of A will depend on the problem. So for a particular problem, we can compute these deltas. We have an explicit expression of this delta. And if it's positive definite, we see that it's more interesting to take a larger value of A in order to reduce sigma 1. If it is negative definite, so it's the opposite, and you should take a smaller value of the moment of A in order to reduce this asymptotic variance. So this is that's all for this central limit theorem and analysis of the fluctuations of the algorithm. And so I'm just recalling the main contributions of our work and give some ideas about future work. So the first point first, we introduced and analyzed a continuous time version of the algorithm. So this is an interesting idea based on the ODE method. We introduced this continuous time system, which is a relevant approximation of the Adam algorithm. We analyze it. We show the existence, the boundedness, and the convergence towards critical points of this objective function. We gave some convergence rates of this continuous time dynamical system by using some Lojasiewicz inequalities, inequality assumption, which is quite mild assumption. And second, we used this continuous time analysis in order to derive some convergence results. So this is what we've called a long-run convergence results of the Adam iterates in the constant step size. So this is the original form of the Adam algorithm. And finally, we've introduced a new version of the Adam algorithm with decreasing step sizes. And we've shown how we can use dynamical systems in order to analyze the discrete time algorithm. So we've shown the almost sure convergence of the iterates of the Adam algorithm towards the critical points of the objective function, capital F. And then we further analyzed the fluctuations of the iterates xn around x star by means of a central limit theorem. And of course, these results open the way to many different research directions. So one of them is to analyze the convergence rates in discrete time. So we have a follow-up work on this question regarding the Adam algorithm. And of course, we can ask ourselves if this kind of adaptive algorithms such as Adam, and of course, more generally, we can follow the same analysis for Adagrad, for similar algorithms. We can ask ourselves if we can avoid some traps. So do we converge exactly to only local minima, or can we converge to some saddle point, or can we avoid some saddle point undesirable points? And finally, can we say something about the non-differentiable case, which is of most important to us because of course, of the deep learning applications. So finally, we find some references here about the work I've just presented. And thank you.